This is our team, Deep Drawing, going to give a presentation on the topic Physics Behind Deep Drawing. So this is our team members, and next slide please. So let me explain first in brief the mechanism of deformation. Mechanism of deformation. The deep drawing mechanism is a complicated process, particularly when it comes to the different types of stresses on each region in the blank. To facilitate the understanding of the mechanism, let's divide into three regions. The outer annular region is sandwiched between the die at its bottom part and the blank holder at its top part. The inner annular region is not in contact with either the punch or the die, and the central region of the blank is only in contact with the punch as illustrated in the figure. When the compressive force is applied to the punch, the draw proceeds material in outer region, which starts to draw progressively inward towards the die profile under the effect of the applied tensile stress, resulting in continuously decreasing the radius in the region, which causes induced compressive hoop stress. The hoop stress causes an increase in the material thickness at the outer part of the region. Unless holding down pressure is applied, the induced hoop stress will cause the blank to fold, which causes wrinkling. So the mechanism can be summarized like pure radial drawing between the die and the blank holder, bending and sliding over the die profile, stretching between the die and the punch in the clearance zone, bending and sliding over the punch profile radius, and stretching and sliding over the punch head. So that's all. Over to next.
The physics behind deep drawing. The metal forming physics of such a shape as well as understood. Since a curve is defined by a few critical dimensions such as the diameter and the depth, the thickness of the sheet is also a consideration. A deep round curve can easily be drawn from a circular blank by considering the ratio of blank diameter to the diameter of the curve to be drawn. Further process will be explained by Amisha.
Thank you, Nitin. Good afternoon, everyone. Here is the table that shows reduction ratios for simple round cups for a given thickness to successfully deep drawn just about any size or depth of round cup shape. A round blank can be drawn and redrawn many times using multiple deep draw operations. Next slide, please. Here it is an example of a typical deep draw process for a deep round cup shape. The deep drawing cup test is a sheet metal testing method in which a circular plate is punched out of a sheet metal strip and then formed into a cup by drawing dry. However, for any product shape, it is not a simple round cup. There is no such table that will allow a successful sheet metal forming outcome. More complex shapes cannot be intuitively deep drawn using a simple method or rule. With the improvements in computer-aided design, it has become possible to design unimaginable shapes which meet modern performance and styling requirements, and as such, modern techniques are required to figure out how to deep draw complex sheet metal shapes. Thank you. Now over to Shruti.
Thank you, Amisha. Good afternoon, everyone. In deep drawing process, the maximum deep drawn ratios as well as the spring back behavior of the metal parts are depending on the stress distribution in the part material during the forming process, while exceeding the load limits of failure in the material occurs, which can be avoided by additional force transmission activated in the deep drawing process before the forming limit of material is achieved. This contribution deals with numerical investigation of process effect caused by additional force transmission regarding the extension of the process limits. Deep drawing process has been different from effectable process parameters, which an optimum level of parameters can be identified so that an efficient final product with required mechanical properties will be obtained. The present work is to evaluate the formability of different metal sheets using deep drawing process, in which effects of different sheet and die blank holder angle on deep drawing process observed for sheet metal of 0.8 mm of SS304 and brass and 0.9 mm of aluminium. The experiments were performed by designing the deep drawing tools such as die blank holder and punch. In addition, the numerical simulations are performed for deep drawing of cylindrical cups using 3 levels of previously mentioned forces. Punch forces and dome heights are evaluated for all the conditions. From this work, the formability of different metal sheets is observed for angular geometries of deep drawing tools. Moreover, it has been observed that strain formation is more for the brass sheet and stress is more for aluminium sheets. The material under the die has little change during drawing process. The deformation is mainly concentrated in the circular ring portion of the die plane, which is the main deformation area of the drawing. The deformation in the deformation zone is uneven. Under the combined action of tangential compressive stress and radial tensile stress, the metal is compressed in the tangential direction. The thickness varies from place to place in height, and the thickness at the mouth of the drawn part increases the most. Deep recessed parts with either vertical or sloped walls can be formed. In this type of forming, the die rig employs a rubber pad as one tool half and a solid tool half, similar to the die in a conventional die set, to form a component into its final shape. Dies are made of cast-like alloys and the rubber pad is 1.5 to 2 times thicker than the component to be formed. For man-forming, single action presses are equipped with die cushions and blank holders. The blank is held against the rubber pad by a blank holder, through which a punch is acting in the conventional deep drawing. It is a double-acting apparatus. At first, the ram slides down, then the blank holder moves. This feature allows it to perform deep drawing, that is, 30 to 40% of transverse dimension. That's all from our team. Thank you and have a good day.